Hello friends, and welcome to another adventure in algebra. Today we're going to be talking about 9.4, which is properties of logarithms. Now I want to stress that what we're going to get today comes exactly from the ideas of the fact that the log does the opposite of what an exponential does. So just kind of remind ourselves of that. If I have b, the, wait, yeah, for base for the exponential. Actually, you know what? I wanted to write a title here. Sorry about that. Exponential logarithm. Woohoo. So remember we have that if I have the log base b to the x power equals to some value y, then this is the same as asking yourself, oh, well if I do the log base b of y, I will get x. So remember, logarithms are asking a question. What power do I need to raise b to get y? I need to raise it to the power of x. It does the exact opposite of an exponential. Its output is the exponent. With an exponential, the input is the exponent. They do opposites of each other because they are inverses. Woohoo! Because you notice how they switch x and y? Trippy, right? So, as you may remember from our previous adventures with exponents, there are a bunch of rules for exponents that we use to simplify them. Things like, oh, well, if I have two things of the same base to different powers, we can instead add together their powers. This was what we would do when we run into things like, oh, I have x squared times x cubed. Boom, I can add together the cube 3 and the squares 2 and do 3 plus 5, 3 plus 2 instead and get 5. That's what we were using. As it turns out, there is a law of logarithms, which is the logarithm version of this, which says something very similar. It says that if I do the log base b of two things being multiplied, so notice the multiplication in here, multiplication of two exponentials led to addition. Similarly, logarithm of multiplication is actually an addition of logs. So see how it kinda doesn't work exactly the same? I'm going to need to move this over just a little bit to fix that second log on here. So it's very similar, but in the exponent one, it was in the exponent. And the logarithm one, it's down outside of the exponent, because remember the logarithms produce exponents. Similarly, we had one for dividing. So see how division of two things of the same base led to, oh, I'll subtract their powers. Same thing's going to happen with logarithms. If I have the log base b of m over n, instead of division, I can do subtraction. One thing to be careful about with this one is really, that doesn't look like a word, sorry, I'm going to fix that, minus the log base b of n, is that you notice m, since it's in the numerator, must go first. Order matters. Similar here, m in the numerator must go first. Okay, now for the last one. This one's my favorite. We had, if I have b to a power and then I raise it to another power, exponent to exponent, then I multiply their exponents. And this is probably the most powerful law of logarithms. If I do the log base b of something to a power, which I'm going to use p for power or exponent, then I can just hop the power out. And we're going to use this one a lot. This one's like my favorite because it's like super special. It's very, very useful. Remember, this is coming from the idea that, oh, well, what does a logarithm output? It outputs the exponent. So it makes sense that the exponent will just come out of the logarithm. Let's do some calculating with these. Or rather, let's do some examples. So for these first ones, we're going to expand using the laws of logarithms. Later, we're going to contract. They also call these the log rules or the log laws. Wow, that's hard. Wrong one. So first up, we're going to do I'll have a bunch of sets of these, so let's do 1a. Do the log base 3 of 4 times 18. That'll be equal to, well, I've got a multiplication inside the logarithm, so that's going to be the same as adding outside 4 plus the log base 3 of 18. Sometimes this will allow you to simplify things, especially if one of these two were a 3. Then that would give me something that I could use and actually do the log base 3 of. Let's do the log base 8 of 8x. Speaking of, oh look, this one seems to do the thing I just mentioned. So I'm going to do the same thing, the log base 8 of 8 plus the log base 8 of x. The log base 8 of 8 is 1 because it's asking you how many powers of 8, because that's my base, do I need to make what's inside the logarithm or what I'm doing the logarithm of? Well, just 1 because it's 8. So that's 1. If you need to review that, you might want to go back and watch the 9.3 video if that one kind of stumped you a little bit. Cool. Let's do the log base 3 of 12. I need to close this because it just keeps accidentally opening the PDFs. There we go. No, I don't want to save that. There we go. All right, sorry about that. All right, same thing. So I have base 3. So what I want to do is I want to work a 3 into this. So I'm going to do this as the log base 3 of 4 times 3. That's not a times symbol. Dot 3. So then I can expand this into the log base 3 of 4 plus the log base 3 of 3, because we have multiplication inside the logarithm is the same as addition outside. And we know the log base 3 of 3 is 1. So this will end up being the log base 3 of 4 plus the log base 3. Oh no, wait, I'm doing the log. If I ask myself what power of 3 gives me 3, just the first power. So plus 1. So that's our first set where we're using the first rule. Let's do the second rule. So I want to do the log base 3 of 3 over x. So we have to be careful about order with this one, so we're going to be real careful. So remember, numerator first, and division is the same as subtraction. So the log base 3 of 3 minus the log base 3 of x. Now the log base 3 of 3 is 1, so we'll end up with 1 minus the log base 3 of x. Okay, I need to scroll her up. All right, B. So we want to do the natural log of e cubed over 5. So I'm going to rewrite this using the division rule. So I'll have the natural log of e cubed minus the natural log of 5. Hopefully remember that the natural log is the log base e. So this is saying how many, what exponent do I need to have for base e that will be equal to e cubed? Well, that base would just be 3. So this is 3 minus the natural log of 5. Next up, what's the log of 10 over x? So I'm going to separate it. Remember, numerator first minus denominator. Don't forget your logs. Aha, remember log where there is no base present. We're supposed to know that that's going to be base 10. And so this is the log base 10 of 10, which is just 1 minus the log of x. There we go. So that was our set of using the division rule. So be careful, don't forget to simplify. If you can actually do the logarithm and calculate something off it, you should always do that. Let's move on to using our last rule, the power rule, my favorite one. We're going to do the log base 4 of 7 cubed. So here, since my exponent is 3, I'm just going to hop that out. So I'll have 3 times the log base 4 of 7. Nice and simple, I like it. Next up, let's do the log base 2 of y cubed z. So here we have to be careful and actually use 2 of the rules at once. So I've got multiplication and a power going here. Remember, the 3 is only on the y, so I can't use the power rule here right away because my exponent that I'm interested in is that cube, and that cube is only on y, it's not also on z. So first I'm going to actually have to use the separation of using their times each other, so I'm going to rewrite it as addition first. And then I can use the power rule to hop that 3 out. Now, the reason you know this is going to be correct is because, well, only the y has a cube on it, so only the y should have that 3 out front. If you would have done this in the wrong order, you would have also had that 3 in front of z, but z wasn't cubed in the original. It was only to the first power. So be careful about that. When you start combining rules, be careful about how you apply them. Make sure that you're doing it carefully and using only one rule at a time. Don't try to combine rules because usually that'll mess you up a little bit. Let's do the log base 5 of 3 to the 1/2. So the fact that this is a 1/2 doesn't matter at all. Remember, that's the same as having a root. So if this would have been the square root of 3, we could have done the same thing, rewritten it with the 1/2 exponent, and then hop the 1/2 out front. So we end up with 1/2 the log base 5 of 3. Let's do some more where we combine these rules together because we want to be careful about the order we do them in. I usually use the power rule last and try to use the other rules first. This is just good practice to keep yourself nice and organized. So log base, oh no base. Log of x squared over this cube root of y. Okay, so again, I'm going to use the power rule last because that's the way I always do it, and it helps me keep organized. So notice there's some stuff with exponents. This needs to be written with an exponent, and then I've got division. So I'm going to use the division rule first and rewrite this as a subtraction. So we'll end up with the log of x squared minus the log of the cube root of y. I'm going to take a moment right now and rewrite the cube root as a exponent instead of a radical. So this is the log of x squared minus the log of y to the 1/3 power. And now we're going to be careful and we're going to apply the power rule twice, once to the first term and then once to the second term. So I'm going to hop the 2 out and get 2 log of x, remember this is log base 10, minus 1/3 the log of y. So there we go. There's one where we used some different rules together. Let's go ahead and do another one. I'll do the log base 5 of x over y to the 4th. This one's easier than the one before. I should have did this one first. So again, I'm going to apply the division rule first because again, I want to use the power rule last. So we got 5 the x minus my denominator guy, which would be log of y to the 4th. Then I'm going to hop my powers out. So this one doesn't have one to hop out, so I'm just going to have the log base 5 of x minus 4 the log base 5. Ooh, I missed my base 5 here of y. If you're wondering why you might expand, because sometimes things simplify when you expand. We've seen a couple where, I was able to actually calculate the logarithm and things went well. All right, you ready? Oops, I need to erase this. It's looking kind of bad. Let's do the log base 7 of 7y squared over the 4th root of x. I should have made my parenthesis bigger. Here we go. Looking good. Cool. So I have to be careful. I have more than one thing in the numerator, but I'm just going to take my time and be very cautious as I proceed. I'm going to use the division first because I don't know if you've realized this, but that's what I tend to do. So I've got the numerator, which is 7 times y squared, minus the denominator, the log base 7 of the 4th root of x. So at this next step, I'm going to be careful. I've got some things being multiplied in this one. I've got 7 and y squared. So I'm going to expand this even further by using the multiplication rule. So I'll have the log base 7 of 7 plus the log base 7 of y squared minus the log base 7. And I'm going to apply, or sorry, not apply. I'm going to change from radical notation to exponential notation. Ooh. And now I've got some stuff to do. So this first term, how many powers of 7 do I need to make 7? Well, just one of them. And then for this second term, I can plop the 2 out front using that power rule. And then the last one, I can hop that 1/4 out front using the power rule. And there we go. Completed. So that was expanding. I'm hoping you notice that I tend to use the division rule first whenever it's present, then the multiplication rule, then the power rule. This is just good practice to try to keep yourself organized. If you don't see any divisions, then, well, you don't need to use the division rule, so we're good. Yeah, so that's expanding. And sometimes that does help you simplify some things, like when we get some ones and stuff, you know? Sometimes it doesn't. Sometimes it's better to combine, which is to go the other way. So I'm going to start with some complicated extended log expressions, and we're going to write them as a single logarithm. So I'm going to write two versions of, well, no, just one version of the directions. So we had expand, now we're going to contract, which is usually written as condense into a single logarithm. So we're just going to have one in the end. Here we go. So we're going to start with, I have the log base 8 of 5 plus the log base 8 of x. There we go. One thing you have to be cautious about is make sure that they have the same base before you do anything. Like, watch out for that. If they don't have the same base, you can't combine them. So I'm going to write this as a single log because I'm going to be able to. And I'm going to ask myself what goes in here. So they're both the same base, and I have a plus on the outside of the logarithms. So plus on the outside corresponds to multiplication on the inside. So I'm going to be able to write this as just 5 times x, or 5x. So all I did there was I applied the first law of logarithms, but the other way. I took an addition and changed it to a multiplication. Let's do another one. So let's say I have the log base 6 of 18 plus the log base 6 of 2 minus the log base 6 of 9. All right, we're going to have to be careful. So they're all log base 6, which means we can write this as a single logarithm. We're going to have to be careful because one of them is a minus, which means one of them is going to end up in the denominator, and it's only the one that's a negative. So we'll have log base 6. I'm going to start by just combining these two. So that'll be 18 times 2 minus the log base 6 of 9. And then since this one is a subtraction, I'm going to make this into a division. Now you could have done this all as one step. 18 times 2 over 9. Now watch what happens here. This is kind of cute. So 18 times 2, if we multiply those two together, we're just going to get a 36. Oops, that G got screwed up. And what's 36 divided by 9? Well, it's 4. So this is just the log base 6 of 4. So looking back at the original, the log base 6 of 18 plus the log base 6 of 2 plus the log base 6 of 9, that's a really long way to write the log base 6 of 4, didn't you say? This seems much simpler. It's a good time. Much easier to calculate. Everything should be golden. Cool. Let's do another one. Let's do 2 log base 3 of 5 plus the log base 3 of 2. So here I'm going to have to be careful. Anytime you see a value out front, you're going to have to do the power rule first. So just like before when we were expanding, I tend to do the power rule last. When you're contracting or condensing, we want to use power rule first. Okay, so what I'm going to do is I'm going to rewrite this so that I hop the 2 in to be an exponent. So this is going to be 5 squared plus the log base 3 of 2. My G's are not doing so good. So then since this is an addition on the outside of logarithm, that's going to be the same as multiplication on the inside. So this is going to be 5 squared times a 2. I am going to go ahead and multiply that out just because I think it'll look a little nicer. So 5 squared will give me a 25. And then when I multiply it by 2, that'll give me a 50. This is really the log base 3 of 50. Cool times. I was really hoping this would be something that is a power of 3, so you could undo the logarithm completely, but it looks like no. Let's do another one. Where am I at? A, B, C, D. Oh, okay. So we have the log base 2 of x plus the log base 2 of x minus 3 minus the log base 2 of 3. So we're going to have to be careful. I've got a mix of plus and minuses again. So that means I am going to have to do some calculating and do some very, very careful changes here to make sure that only the ones that have a minus end up in the denominator, because that's the only one that should end up in the denominator. So we've got the log base 2, log base 2, log base 2. So they're all the same base. That's always the first thing you should check. All right, so log base 2, I'm going to just combine these two first. That will be x times x minus 3. Ooh, I don't like my parentheses there. Maybe I'll make this one kind of squarey looking so you can tell them apart. Minus the log base 2 of 3. And then since only this one is being subtracted, it's the only thing that goes into the denominator. So I'll have the log base 2 of x times x minus 3 divided by 3. That one's not very pretty, but that's where it is. Good times. Okay, so now that we've seen a little bit of the laws of logarithms, what I want to do is I want to use them. So we want to use them to do one more thing. So if you have looked so far at what you're able to calculate and you pull up your handy dandy handheld calculator, you should notice that it does have a log button on it and a natural log button on it, but there's no log base 2. There's only the common log and the natural log. So what do I do if I want to calculate something like what we had earlier, the log base 6 of 4? I need something else to help me. What you actually need is what's called the change of base formula. This is actually kind of cool. It's a way to, do a log of a different base using e and 10. So we notice that calculators only do base e and 10. So what this is going to do is it's going to help us do the other ones. So pretend, or for example, I want to calculate, I want to do the log base 4 of 3. I want to know what that is. I want to know the value of this. Is it between 2 and 7, or is it like a 1? I don't know. It's probably some crazy decimal, and it's probably going to be small. I have no I don't know. Let's see how to do that. So what we can start off with is okay, oh boy, the log base 4 of 3 is some number and I don't know what it is. So I'm just going to call it y. Probably could have picked x, but it's too late now. And then I know one trick that I can do. I can rewrite this as an exponential. So what this is saying is that 4 to the y will be 3. And I got to figure out what y is. What power will give me 3 for base 4? And that's all well and good, but that doesn't really help us. I can't do this. I could try guess and check and just put in a couple different values of y until I figured out what would give me 3, because 1 wouldn't work because that'll just be 4, so it's got to be something smaller than 1. And 0 isn't it, because if you put in 0 for y, you'll get 1. So it's somewhere between 0 and 1. I don't know what it is though. There's got to be a way to do this. We're going to see something that helps us. So I have 4y equals 3. And what we're going to do is we're going to use a log we can do on the calculator. So I'm going to use the log base 10. You could have just as easily done the natural log. So I want to do the log of both sides using a base I know, in this case base 10. So by doing that, I'm actually doing something kind of sneaky. So whatever I did to one side, I did the other, so I haven't broken any rules of algebra. Yeah? But I also have the power rule, which says I can hop y out now. So I have y times the log of 4 is equal to the log of 3. And then all I need to do to get to y then is just divide by the log of 4. Remember, a log with no base written is just log base 10. So what this says overall is, oh, well, if I want to calculate y, I can just do the log of 3 over the log of 4. See how this is working? And that you can plug into a calculator. Da 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 da. So there's my log base 10. I'm going to move this over a little so you can see it better. Oh, that is absolutely not what I wanted to do. Thanks, Microsoft. Way to help me out. I'm so mean to it, and it's so lovely to me. So I'm going to do the log. Ooh, I forgot how this does this. So I got 3, and I'm going to do its log. And I want to divide that by, put some parentheses in so it knows I'm going to log first, 4, and I'm going to do its log, close my parentheses, and hit equals. There we go. There's my logarithm. I hate the calculator on Microsoft. Hopefully you have a better one. If you have the TI 30X, which is the most common, you do have to do the thing where like you do log and then 3, close your parentheses, then the do division sign, hit log again, and then 4, and then close your parentheses. Don't forget to close your parentheses. It'll totally mess you up. And I was right. It's somewhere between 1 and 2, slightly smaller than 1. So that's what y is. What was y? It's the log base 3 of 4. So what I just did is what is called change of base formula. So I'm going to take what I just wrote and rewrite it in a way that lets you do it for any base. Okay. So if I want to do the log base b of something that I'm just going to call capital A, what I can do instead is do the common log, the log base 10 of a, and divide it by the common log of the base that I have of b. And that will give me the value. Or if you want, it'll be equal to the natural log of a over the natural log of b. So if you have a calculator that does natural log but won't do log, you can also do it with natural log. It really doesn't matter. So that's our big like formula result from this chapter. Let's use it. So we're going to calculate using the change of base. So what I would suggest you do for this next set of examples, I did not mean to pick up and move that, I wanted to move my page up, is that I'm going to write how I do these and then write the result. What I would suggest you do is pull out your calculator and calculate along with me. Make sure you get the same results I do, because if you don't, that's troublesome. So I'm going to do the log base 6 of 14. So according to change of base, I'm going to do log over log, and base goes on the bottom, so the 6 goes down here. And that's how I remember this. Base goes on the bottom. Cool. So now if you pull out your calculator and do log 14 and divide that by the log of 6, you should get 1.472, some 8s, a 5, a 9, and then a 4. I'm writing as many places my calculator will give me. That way you can be sure that yours is correct. Let's do the log base 9 of 27. Now, this one you totally could do using other means, including, rewriting this using radical exponents, but I'm not going to do that. I'm going to use change of base formula, and you'll see how this comes out as a fraction. So, log base 9 of 27, here we go. Base goes on the bottom, so 27 goes on the top, log on the bottom, I gotta put my 9 down there. When you do that, you get 1.5. Or if you like fractions, that's 3 halves. So thinking about what's happening here, 1.5 power of 9, like sneakily 9 to the 3 over 2 is the same as the square root of 9 cubed. So the square root of 9 is 3. And then when you cube it, you get 27. That's really what's going on here. So that's why it's 3 over 2. Anyway, that one's a little tricky. I hope you enjoyed it a little, maybe. I don't know. Let's do the log base 7 of 15. For fun, let's do this one with natural logs, for no reason other than because we can. So natural log, remember base goes on the bottom, so 7 on the bottom, 15 on top. Plug that into your calculator like I am right now. Natural log of 15. Oops, I hit the wrong button. Natural log of 15, not 16. Divided by the natural log of 7. Don't forget to close your parentheses if you've got them. And then you get 1.31, I can read, 662509. So if you've ever wondered how you might want to calculate something where the base wasn't given to you, and you looked at your calculator and thought to yourself, oh my, I don't have the bases I need, here's how you can fix that. I hope you enjoyed this lesson. Try applying your laws of logarithms to expand and contract. And don't forget, you can always change your base, but base goes on the bottom.